Hello everybody, welcome back to Computer Science 4300. Our lecture was cancelled on Tuesday. I was not feeling well, and so that happens sometimes, apologies, but I just shifted everything forward. We were going to have one blank lecture at the end anyway, and so might as well just put it where we missed our lecture. So today we are right here, and we're giving one of the coolest topics that I love talking about, which is cache coherency and memory pooling. So turns out that everything you learned about computer science is wrong, and today we're going to figure out why that is. So that might be a little bit of an exaggeration, but you may not feel like that once the lecture is over. So let's jump right into it. Oops, my PowerPoint is appearing on the wrong monitor again, so give me 1 second. Where is view? There we go. Perfect. So, lecture 19, game performance, memory pooling, and CPU caching. So, there are many different factors that go into the overall performance in our game. And actually, in the next lecture, I'm going to talk about benchmarking so we can see exactly where the bottlenecks in our game might be. With ECS, we can profile our systems independently and determine which are bottlenecking the program's speed. So for example, our typical bottlenecks might be our physics system, our AI system, our rendering system, raycasting, whatever. So the good thing about ECS is that we have individual systems that do those things, and we could very easily say comment one out and test the game without rendering it and see how much faster we run and see how much time in each individual system takes, etc. And so we have profiling tools out there that enable to do things like this. And actually, in the next lecture, we'll be looking at a tool just like this, and we'll be creating it from scratch, which is even cooler. So there are lots of videos out there for doing this sort of thing. Here are just some that I've included in the slides. And our next lecture is actually going to be talking about visual benchmarking in C++, how we can profile our code in really cool ways, etc. However, there may be some non-obvious performance hits in your programs, especially if you're moving from a language in which it, like if you used Python or Java or any of these languages before, it managed all your memory for you. So you may not have been thinking about memory at all up until this lecture. So it's easy to think that the only things that affect performance are the algorithms and the math, right? Get a better algorithm, get a more optimized function. This is somewhat true, right? If you have an n-squared algorithm and you turn that into a log n algorithm, that's going to have way fewer iterations, right? So yes, algorithms are important, but it turns out that in the real world, you don't use fancy algorithms a lot. You just don't get a chance to, right? You're going to call whatever sorting algorithm is in your library because you know it's stable. Any really hardcore algorithms are going to be in some library that you've either created and benchmarked independently or some library that you're just using that someone else with a PhD wrote, right? So it turns out that there's not a lot of places where you actually get to use fancy math or fancy algorithms in your everyday programming. In practice, however, the implementation of those algorithms and how you store your data can impact the performance even more than the choice of algorithm, which seems a little bit counterintuitive because, you know, you should be fourth year computer science by now, and up till now you've been told that literally everything that matters is just the choice of algorithm, but that turns out not to be true. So there are some important optimizations that you can make. And the first one is use more efficient algorithms, right? So this is where computer science helps, but it's kind of where computer science stops helping as well, because computer science is not a software engineering degree, and oftentimes you don't get told about important things like memory and cache coherency and stuff like that. So your computer science degree is probably going to stop helping you at that point where your algorithms are their most efficient. You could also minimize the size of your data structures, right? So if you have smaller data structures, then it'll take less memory. That's good. We can talk about code reuse and modularity. So reusing pieces of code that we can optimize in individual in functions and then use those optimized functions later. We can also minimize dynamic heap allocations. So we'll talk about this toward the end of this lecture with memory pooling. And we can also write cache-friendly code, so data-oriented design and programming. So minimizing data structure size. Well, C++, unlike some other high-level programming languages, gives us really fine control over the size of the data structures that we can use for our games. So we can say, hey, this thing is a 32-bit int, or a 16-bit int, or a char, right? Like 256 possible values. Deciding on a size type for your data depends entirely on the context of your game, your function, your structure, etc. So minimizing data structure size can help your game in several different ways, not just memory. So a few of those ways: if you reduce the size of your data structures, you use less memory, so you use less RAM. That's obviously good, right? We want to use less memory. But also, reduced size means less time copying data. If data needs to be copied in your program, this can dramatically reduce the running time of your program. So for example, if you're storing things in vectors and you run over the size of a vector, your vector has to resize and you have to copy all the data in that vector. So if you have less data to copy, this can mean less time copying as well. And another really cool thing, if the size of your data structure is actually less than 8 bytes, then you can pass by value instead of by reference. And that elimination of dereferencing on functions calls helps cache misses, helps all sorts of things. So if you can get to the point where some of your data structures are actually very small, passing them by value gives you a lot of speed up as well. So here's an example. If you've taken Computer Science 3200 with me, you might be getting PTSD from this image. But let's just say you have a game world, right? And that's size 64 by 64. And so if it's size 64 by 64, your default computer science brain might say, okay, how would I store the player's location? Well, I'm just going to have an int for the x and an int for the y, right? But in this case, if you know that your map is size 64 by 64, and it's not going to get bigger than, say, size 256 by 256, then you could actually store the player's position, x and y, with an unsigned character instead of or unsigned char, instead of an int. And so you don't need the full 32 bits of an int to store this x and this y. You could just use a uchar. But the problem here with premature optimization is, let's say you did do this optimization and later there were huge maps that were like tens of thousands of tiles wide or whatever, then this premature optimization means now you have to, okay, I actually need a bigger value to store things. So what I'm recommending is that, yes, in your first pass, when you make everything work, just use integer values, right? Don't prematurely optimize things. Once your game is finished, like the spec of the game is finished, and you know what the maximum size of a map is, or the maximum size of the player's health, or whatever, then go back and start optimizing things. Don't assume from the start that you can use a char when you should have used an int or something like that. So that's just very, very basic data size, right? Like, don't use gigantic 8-byte values where 1 byte might do. Okay, code reuse and modularity. We've talked about this a bit before, but basically, whenever you're doing any programming, unless you are doing very hardcore loop unrolling optimization type stuff, which we won't get into for this course, put any reused code into its own function. So for example, if you have any piece of code that you are going to use in more than one place, don't copy and paste that code into 2 places. Make a function. And then what happens is, if, you know, a couple of weeks later, you get a bit smarter and you want to optimize that function, then you can optimize it in one place. So if you take all that code that you were previously copying and pasting all over the place, and you put it into its own function, well, like I said, let's say that I thought of a new way to make that code run faster. Well, now I only need to optimize it within that function, and not in the 10 places that I'm using that function. And we have a good example of this in the memory manager. So we use the memory manager all the time. Oh, excuse me, I'm just turning off my phone notifications. And so we have this memory manager where we've done all of our, optimizations and stuff. And we can use the memory manager all the time without having to know how it works or how it's optimized under the hood. And any optimizations or changes that we make to the entity manager, that's invisible to anybody using the entity manager. So it not only helps for optimization purposes, but it helps with just keeping all this stuff in your head. You don't need to know how the entity manager, you just need to know add entity, right? Or get entities. And it doesn't require any top level changes to your code. So optimizations can take place at the code understanding and use level as well, not just at the did this run faster. All right, next we have minimizing dynamic memory allocations. So far we've been talking about, or at the beginning of the course, we really sort of drilled home the difference between heap allocations and stack allocations. And heap allocations are very, very expensive. They use this function called malloc, which is memory allocation, and that's operating system dependent, okay? So Windows will have a different way of looking up memory than Linux, etc. And the reason that it's a little bit, or one of the main reasons that it's pretty expensive is because it tries to find a contiguous block of memory of a given size. And if your memory is super fragmented, then it may take a while to find that contiguous memory. And so given the complexities of memory layout, it's much, much, much slower to use dynamic memory allocations than it is to use stack allocations. So just as an example, over here on the left, this is a flow chart of the logic of malloc. Okay? And this is the Linux version of malloc. It's not just scan the memory and look for stuff. There's a lot of stuff going on inside of malloc. So whenever you create a shared pointer, this is happening. Okay? It's really kind of bad if you think about it. So we don't want that to happen. Whenever you free something, this is happening. And so we want to minimize the amount of times that this happens. And we are going to be creating a lot of entities in our games, right? And we would want to be able to create, hundreds, if not thousands of entities. Rip my bit rate here. I'm sure my face is all pixelated right now. But we would want to be able to create a game like this, right? And have this sort of performance where we can create tons and tons of entities. And so this right here, what you're seeing, I created a version of our game engine with the memory pooling system that I'll show at the end of this lecture. And this is what it's capable of doing. Thousands and thousands and thousands of entity creations and deletions every second. So what is memory pooling? So heap memory is slower to allocate. It's very, very, very slow to allocate heap memory. But the problem is we need heap memory because the stack memory is too limited. You only maybe have a few megabytes, right? So what we can do to solve that problem is to allocate a large chunk of heap memory at the start of your program and then only use that space, right? So this is going to eliminate memory allocations during runtime. Sorry, dynamic heap memory allocations during runtime. But what it does is it adds the complexity of managing the memory pool and where to put new objects. So what you do is you say, okay, at the start of my program, when I have my loading screen or whatever, what I'm going to do is allocate, here's a gigabyte of RAM or something like that. And you can allocate that huge contiguous chunk of memory. And then instead of using the system's dynamic memory allocations, you can just use that memory pool, and then that'll be much, much faster. And I've got Freckles is over here, my cat. He is crying very, very loud, so I'm going to let him out really, really quick. Just one sec. Here's Freckles. He wants to say hello. I don't know if you can hear him or not, but he's been waiting to get out for a little while. So I'm going to go let him out. Just one second. All right. Freckles is safely outside in the rainstorm that he wanted to get out. So, what was I saying? Memory pool. What we can do in order to help eliminate those dynamic memory allocations is pre-allocate a big chunk of memory with one big malloc at the beginning, and then use that memory ourselves and manage it ourselves so we never have to call that heap allocation again. Yes, Freckles is quite a lad. People out in the chat talking about Freckles. All right, so that's what a memory pool is. The memory pool can also help us with something else, and that is cache coherency. So writing cache-friendly code is one of the most important speed optimizations in practice. When data is fetched from RAM, you don't just get the variable that you looked up. You also get a bunch of surrounding variables that are stored in the cache. So let's say, for example, in the top level fastest cache, you might get 64 bytes in every fetch, okay? So if you're just fetching an integer, which is 4 bytes, you actually got 16 integers into your cache. We'll talk about examples of this in a little bit. Cache memory is much faster, physically closer. It is also much smaller than normal RAM. And so if you organize frequently used data contiguously in memory, meaning right next to each other, that allows you to fetch, it allows your cache to fetch more of it on each lookup. And so when RAM is not in cache, it's called a cache miss. Now, there are multiple different levels of cache memory in your computer. We're not going to go into the specifics of all of them, but what we do want to know and what we do want to do is that if your data that you're accessing frequently is contiguous in memory, then when you go to look up those contiguous variables, let's say in a loop or something, they will all be in the cache, or many of them will be in the cache. And so you will be able to get this very fast, very expensive, very close to the CPU memory, rather than having to go all the way to the RAM. And so you may say, okay, Dave, like that sounds great, but how much time does it actually save from that? Well, let's have a look. Cache misses are surprisingly effective. So if you look up, let's say you have an array in RAM somewhere, and these values are not identical for every computer, but the point I'm trying to make is approximately the same for most computers. If you look up something in RAM, and it's not in the cache, that's about 200 CPU clock cycles to look up that thing. If it is in RAM, if it is in cache, sorry if I said in RAM, if you look up something in RAM and it's not in cache, that's a cache miss, it costs you about 200 cycles over the near instantaneous lookup in about 2 cycles of something in the cache, okay? One multiplication of 2 integers is 3 cycles. So you can do 65 multiplications in the same time that it may have taken you to look up a variable's value in RAM if it's not cached. 65 multiplications. So think now about how important your algorithm was. Let's say you spent 10 years making it so you eliminated half of the iterations from your algorithm, right? Well, now it's only 30 times slower than it could be and not 65 times slower than it could be. Like, this is a huge cost. And you can literally make your game run tens of times faster by writing cache-friendly code. So let's just have a look at an actual example of this. Here are 2 loops. We've got some big array, okay? So we've got a big array. This is 64 megabytes of data. Okay, so we've got an int array, 1024 by 1024. That's a megabyte times 64. Now, what we're going to do is we're going to have 2 different loops. The first loop is going to multiply all of those values in the array, all 64 million of them. We're going to iterate through the array and multiply the value by 3. That's it. In the second loop, we're going to loop through the array, but instead of accessing and multiplying every value by 3, we are going to multiply every 16th value by 3. Okay? So just out there in the chat, I want to give you like 30 seconds. How much faster should this loop run than this loop? And I want you to give your honest answer. How much fast? So this loop does 1/16 of the work, right? It's doing literally 1/16 of the work. 1/16 of the multiplications. So how much faster should it run than the other thing? All right, someone said 16 times. That's perfectly reasonable, right? If you're looking at this, you're saying, okay, well, maybe adding 1 is a little bit more efficient than adding 16. I don't know. So maybe there's a little bit of something strange going on here. But, and so like this should ideally, in the computer science theoretical view, this should take 16 times longer than this. But it takes the same amount of time. Literally. It does 6% of the actual work, meaning 1/16 of the multiplications, but it takes literally the exact same amount of time. What? So let's have a look at this. If we take this variable, 16, and call that k, all right? So it could be 2, doing half the work, 4, 1/4 the work, 16, 1/16 the work. Here's a graph. Here's a graph of how long it takes that function with different k values. So if I multiply every single value in the array, or I multiply half of them, or 1/4 of them, or every 1/8, or every 16th, it takes the exact same amount of time. Why is that? Well, it's because on this system, the cache is 64 bytes. So whenever I look up an integer value, the cache gets that integer value and the next 16 values. Okay, do I have a slide explaining this? No. Oh, yes, I do. Okay, so why is this? Well, memory access dominates the running time. So the cache is grabbing 64 bytes, which is 16 integers. Remember this value, 16? So loop 1 has 1 normal lookup, meaning a cache miss, and then 15 cached lookups, right? Because it gets the first one and all the next, and then the next 15 are basically free. Loop 2 has 1 normal lookup, but it has 1/16 of them. So if this is doing 1 200 cycle cache miss and 15 2-cycle cache hits, that's 230 cycles. But loop 2 is doing 1 cache miss, which is 200 cycles. And the multiplications don't even matter, right? All the multiplications are actually pipelined, meaning that the multiplications can be done almost at the same time. So I'm not going to get into what pipelining is, but it's a form of concurrency. And basically, at a lower level, all of these, like maybe like 8 of these 16 multiplications are being done like at the same time. And so the multiplications here are not the bottleneck at all. It's actually the looking up of the data. And so what happens is, once you get into 32 things, then you're literally doing half of the work of the 16, because you're getting all of these, like from 16 onward, every lookup is a cache miss, okay? Or at least the like highest level of cache. So up to 16, all of these, everything is already in the cache. After 16, everything is a cache miss. So only then do you finally start going down in time. So just realize that the thing you think, oh my god, my game is going to run so much faster if I just skip every few pixels or something like that. No, like that is not the case whatsoever in some case. So that's like a bit of a wake-up call. And here are more cache examples. There's a gallery. So this graph here and many, many others, if you're really interested in this, and if you are a programmer, you should be interested in this. There's a gallery of many more processor cache effects that really illustrates this. And there's a great video here on data-oriented design in C++ and writing cache-friendly C++ code. This is like a CPPCon talk that is quite wonderful. And we'll talk about some of the things that we're going to talk about for the rest of this lecture. But Mike Acton here has way more actual experience than I do in the industry, so he gives some industry tips that I cannot. So cache-friendly data structures. In order to avoid those cache misses, we want to store data contiguously in memory, right? This is the takeaway from all of this. Arrays and vectors store data contiguously, but it is not guaranteed that lists, sets, maps, or dictionaries don't. In practice, most of these structures do not store data contiguously. So linked lists typically do not. Sets typically do not. Maps typically do not. Dictionaries do not. And so, if you're storing your data in one of these data structures, you're going to get far more cache misses than if you store them in arrays or vectors. And so linked lists, for examples, they often use pointers to heap allocated memory, which is really, really slow. And so if you can, use vectors or arrays wherever possible for your data, okay? But note, vectors are dynamically sized arrays, meaning that my vector is initially going to start empty, and then when I start adding stuff to it, it's going to have to grow, right? So it had 0 things in it, then I put 10 things, maybe 1,000 things. It's going to have to grow. It's not some magical thing. So what happens is, when a vector is filled, internally, it has to create a new, larger temporary array and copy everything over, right? So let's say I have an empty vector. I add something to the vector. Well, it was previously empty. It had no room for anything. So now it's going to say, okay, only at the time when I want to add my first thing, let's say I'll give it a capacity of 10. I don't know, some value. It has to choose some value, which is how much memory it allocates to put stuff into. Once I put my 11th thing into the vector, well, now that vector is full. I can't just add memory to the end of it. That's not how it works. Like, that memory might not be available for me. And so there might be other variables there, etc. So I have to go to the heap. I have to say, okay, maybe let's double the size of the memory. So give me 20 things that are contiguous. Give me that memory, and now I'll copy the 10 things that I did have into this new size vector of 20, and then add my 11th thing. That's literally what's happening. Okay, is that every time your vector fills, there's this hugely expensive copy. So avoid vector resizing when you can. And the way you do that is that you can reserve an amount of space equal to some maximum size. So let's say, for example, you want to, you're using vectors, which is fine, but you know that you're going to store at most 1,000 things in this vector. So what you can do, if you can spare the memory up front, you can say vec.reserve some maximum number of elements. And what that does, so you create the vector, then you reserve an amount of space for it, and it uses a single malloc, and all the RAM is used immediately. So even if your vector has nothing actually in it yet, it still has allocated the space for 1,000 things. And so what happens is, if you do 1,000 inserts into that vector, it will not do any resizing because it has space for 1,000 things, right? So typically, when you create a vector, you want to reserve some maximum size so that you are reducing the amount of dynamic allocations. But of course, that's a trade-off because you're using the memory immediately, okay? So, not only do we have to choose, okay, do we reserve stuff with a vector, but what data do we actually want to store in our vector? Okay, well, let's just have a look at a couple of different storage options. Let's say we have some data structure. Let's say this is like a struct, okay? And that struct is, I don't know, the data that's in our entity, right? For example. So maybe we have like 100 bytes, or Jesus, 100 bytes. We got a lot more than that. Let's say we have a kilobyte of data in our vector, just for an example. So storing the raw data in our vector makes it contiguous. So that's good, but raw data is larger, which is more expensive to copy, which is bad. So maybe we might say, okay, maybe we want to have a vector of pointers to data. Well, that has trade-offs as well. So storing pointers to data usually means that the data is not contiguous. These pointers are easier to copy, but they're not necessarily cache-friendly, unless the data that it points to is intentionally contiguous or pooled, which is not usually the case. And if this is a shared pointer, everything is going to cache miss. Okay? So if we have shared pointers to our entities in a vector, every single time we look up an entity, we're going to get a cache miss. And that's currently happening in our system, right? So right now, Entity Manager has a vector of pointers, well, actually shared pointers. And so every single time we get an entity, we get a cache miss, which now that you know is really, really slow. So let's see what we could do about that. So this is kind of an illustrated look at what the last slide just said. In the first case, we are storing our data contiguously in a vector. So whenever we look up, say, this piece of data, let's say that our data is sized so that whenever we look up something, we get two things in the cache. Okay, so we're cutting our cache misses in half. That's great. Contiguous data allows us to fetch multiple pieces of data. Down here, if we store pointers to data, the pointer values are cached, but not the data that it points to. Because this data, this data over here that this points to might live over here in memory. This one might live over here in memory. This one might live over here in memory, right? So we're not actually caching like the XY values of our position of our entity. We're just caching the pointers. And so here's a big trade-off. I got to get rid of these marks. And the trade-off is, if we want to move data around inside a vector faster, we would want to store pointers. But if we want more cache-friendly stuff in the vector, we want to store data. Okay, so that's just another trade-off. Everything is trade-offs. Let's talk about our ECS system and caching and what we can do with ECS. And this ends up being one of the most powerful parts about ECS, in my opinion. So entities are containers for components. That's what we've been extolling the virtues of this since day one, right? Entities are just containers for components. Right now, entities are currently storing all component data in a tuple, which is contiguous. That's great, because it means that if all of the entity components fit within the cache line, the entire entity is actually cached for us. That's really cool. So whenever we look up an entity, sure, there's a cache miss because it was a shared pointer, but all of the data, the component data, is stored contiguously within the entity. And so that means when we look up component 1, we also have component 2 in the cache for free. We also have component 3 in the cache for free, maybe even component 4 if they're if they're small enough. So we almost have this entire entity in the cache for us, which is pretty cool. But that sounds cool on the surface, but is it what we actually want? Well, let's investigate that. So this is what's happening. We have our entities. We may have these entities that are cached, right? If entities are stored in a vector, they are contiguous. So we may have entire entities, like 2 entities in the cache. But currently, we're storing shared pointer of entity. But let's just pretend that we weren't storing shared pointers to entity, and we actually do have this sort of structure going on, okay? So let's pretend that we're doing that. Entities are stored contiguously. So that means if I have entity 1 and entity 2, if I look up an entity, I may have the entire entity in cache because the entity's data, the components, are stored contiguously within the entity. So just look, I have my cache here and it's filled up with component 1 of entity 1, component 2 of entity 1, component 3 of entity 1, component 4 of entity 1. However, the components are not contiguous. Like, each component of the same type is not contiguous. So here's something that we have to decide. Do we actually want the entire entity in the cache line? Or maybe we want something else. Well, let's have a look, right? Let's have a look. Storing entities contiguously makes sense, right? It intuitively initially makes sense because now the cache may have multiple entities in it. However, cache coherency is all about access. How we access the data inside our entities determines how we should store our data. And that YouTube video that I linked by Mike Acton at CPPCon, it's all about this, okay? So how we actually access the data is the most important thing for cache coherency. So let's look at some examples of the systems that we actually have in our game to see how we are accessing our data. Let's look. Well, here's our movement system. For example, we have, for each of our entities, take the velocity and add it to the position. That's the whole movement system, basically. Here's our rendering system. Draw the sprite. That's it. Draw the sprite. Here's our collision system. Do something with the bounding box and do something with the transform component. So let's color code this. Here we go. The movement system is only looking at the transform of an entity. Okay. The rendering system is only looking at the sprite of an entity. Okay. The collisions are only looking at a little bit more data. Maybe the bounding boxes, maybe the transforms. So that's interesting. We're only looking at, in each of our systems, a small portion of the components of an entity. So we may actually not want the entire entity to be cached because it's not helping us. We're not looking at any of the other components here, right? So it doesn't matter that the whole entity is cached. So ECS systems usually only access 1 or 2 different types of components for each entity that they actually operate on. So given that access pattern, we would want to store similar components contiguously rather than entire entities contiguously. And components are small, so the cache line can fit many, many more components in the cache than full entities in the cache. So this is what we looked at before, right? Where we have a whole entity in the cache. But as we saw, what we actually want is to access entity 1, component 1, and then entity 2, component 1, because we're looping over all the entities and only accessing maybe one of these components. So this is what we would want, is that each cache hit hits a bunch of the same component type, not the whole entity. So ideally, this is what we want to have. So ECS systems operate on similar components, and if the components are contiguous, we have more cache hits. How can we achieve that? Well, let's go back to our idea of this memory pool. So a memory pool is a pre-allocated chunk of data, of memory, that we will use for storage of whatever we want. Okay, so for example, we can store entities in a memory pool. By pre-allocating the space, we don't need to use any dynamic memory allocation. But we may need to know the maximum size beforehand. But the cool thing about the memory pool is that we can organize the data however we want. So let's say we have a memory pool. And what I've done here is I have created this table. And in this table, this is going to be a vector of entities. Okay, so our memory pool is a pre-allocated chunk. Let's say we have 10,000, a 10,000 length vector where we can store entity data. So each column here is an entity. So I've got my first entity, that I've inserted into the memory pool, it has component 1, component 2, component 3, and component 4. The second entity in the memory pool is this column, right? So if I have a vector of entities, then each column is stored contiguously in memory, right? So the entity is stored contiguous in memory. And this is kind of what we have right now in the memory, in the entity manager. Now, we're storing shared pointers, so it's not what we're actually doing. But if we weren't storing shared pointers, if we were just storing raw entities, this is kind of what we would have, is every column in this table is a entity and all of its components are stored contiguously. So what we get is this, right? We get a big data structure, a vector of entities. So what we can do here is that this memory, all this space is allocated right at the start. So we have some maximum size. Let's say we know that we're never going to have more than 10,000 entities on the screen. So we have this vector of size 10,000. And now when I add entities, I don't need to go out to the heap and call the operating system function to look for memory. I just say stick it in the next spot. Next entity, stick it in the next spot. And then I can fill up my memory pool however I want, and it's so much simpler. And none of this gets dynamically allocated, and none of it gets dynamically deallocated. So the first thing that the memory pool offers us is way faster entity creation and way faster entity deletion. And I'm actually going to go through like an illustrated example of this in a bit. So the memory pool can eliminate all runtime dynamic memory allocations by being big enough to fit all the entities. So we trade upfront memory for runtime speed. When a new entity is created, all we need to do is find an empty spot for it in the table. And so that in practice is much faster in malloc. So for example, we can just scan left to right for available space. And when an entity dies, I just mark it as available. And so I don't need to delete data anymore because all I would need to do is just mark this column as free. And then when I'm scanning, oh, that's a free one, stick my new entity here. Excuse me, I got the hiccups again. But we just talked about how we don't want entities to be contiguous. We want to have components be contiguous. So instead of columns being continuous, let's change it so that the rows are contiguous. How would we do that? Well, we're going to have like this. So instead of having a vector of entities and then entities storing components, now what we have is we're just going to have a bunch of vectors of components. So our memory pool is just a bunch of vectors of components. So each row now is contiguous. And each entity ID is the index into this vector. So components are stored separately, but within each component, they are stored contiguously. So this means, look at this, if each row is now contiguous, then what is an entity? If the entity no longer stores the data, well, it no longer stores its components as member data. All the entity is an integer index into this memory pool. Look, all the entity does is say what index of each of these vectors it actually wants to access. So entity 3 doesn't store any actual data. It just says look up index 3 in all these vectors, and that's my component data. So entity functions will now access our memory pool and look up the data at their associated index rather than storing the data. Well, how the hell could I implement this in C++? Well, there's a very easy way to implement all this. So the way I can do this is, look, we had a tuple of components stored in each entity, but instead of doing that, let's make a tuple of vectors of components and store that in the memory pool. So, or the entity manager, wherever you want to do it. So this is called an entity component vector tuple. I'm just calling it that, right? It doesn't have an official name, but you have a vector of type component 1, a vector of type component 2, a vector of type component 3, etc. And the way that tuples work is I can get access to that vector of a particular type by saying standard get standard vector of type T on data, right? If I have a entity component vector tuple created, and then if I want to get access to that particular entity's data in that vector, well, it's just stored by the index. So if I want to get access to, say, entity 4's, the entity with ID 4, its transform, then I would say standard get standard vector C transform data indexed by the vector by the entity ID. It's really cool. Like, it just lets us do that for free. So here's what our entity pool looks like now. Our entity memory pool is going to store a few different things. So this would be an actual implementation of a memory pool if you want to do that. So we're going to store the number of entities that we've created so far. We're going to store the actual memory pool itself, which is the vectors of components. We're also entities also have other data. They may have tags, whether or not the entity is active. So instead of now having a vector of entities and the entity storing all of its own data, we have many vectors and the entity just storing where in those vectors to look up the data. So whenever we start the memory pool, we would have this, maybe it could be a singleton, because we wouldn't want to have multiple memory pools. That's going to be started up with some maximum number of entities, right? So maybe we know that, okay, we're never going to have more than 10,000, so initialize this to be of size 10,000. And if we ever want to get a component of an entity, well, our entity is going to have an ID, and just like before, we can just create a templated function that returns standard get standard vector T on data indexed by that ID, right? Similarly, if we want to get the tag of an entity, well, then we could just return the tag of an entity from the tags vector. Super simple. Then inside the entity class now, literally the only thing that an entity stores is its ID. It's just an integer now. An entity is just an integer. Isn't that crazy? And the way we would write the function for getting, if we have this singleton memory pool, then in order to get the component of a given type of an entity, we just return entity memory pool, the instance of that memory pool, dot get component of the type with the ID of the entity. Or if we want to say has component, we just call has component on that. So all of the data now is no longer stored in the entity class. The entity class is just an integer ID with functions to go look up that data when we want to. And so inside the entity manager, we have to make a change as well. So inside the entity manager, we no longer need shared pointers to entities. Because entities are literally just integer IDs, we can just pass entities by value if we want to. So now we can store a vector of entities instead of a shared pointer to an entity. So if I want to add an entity, well, I have the same function inside my entity memory manager or my entity manager, except now, instead of just creating standard make shared to create the entity right here, it would have to call add entity with from the memory pool. And then it would get this entity that's returned from the memory pool and just return that, okay? And inside the memory pool, how do we actually add an entity to the memory pool? Well, we would just get the next entity index and return that index. It's crazy. Well, I mean, we would have to set all the vector indices to 0, but it's crazy how easy this is to actually accomplish with ECS and the system that we've been doing. So when we create the memory pool, now there's one other thing that we have to worry about. What we have done is we've created many copies of blank default constructed components of each given type, right? So each component has a Boolean associated with it, whether or not an entity actually contains that component. And entities also have an active Boolean. So let's look at what our memory pool would look at the start, okay? So we've got vectors of components. Each of those components are going to have their default values constructed, and they also have a Boolean value which says whether or not, like true or false, whether or not the entity actually contains this component. So a newly constructed entity doesn't have any components added to it yet. So all of these things will be false by default, right? It doesn't have entity 1 or component 1, it doesn't have component 2, it doesn't have component 3. The tag is going to be blank and it's not active, right? All of these entities, they're not live entities in the game. They are just blank entities that we've put in the memory pool because we need something there to take up the space. So whenever we want to put an entity into the memory pool, we just need to find a location for it within the memory pool. And the fastest and simplest way to do that is just scan from the beginning of the pool to the end of the pool and find the first location of a non-active entity and use that slot. So let's say that we have this, which is our initial blank memory pool, and we want to add an entity. So what we do is we call entity p equals entitymanager.addEntity with a tag of p, right? So here's what we had before. All it's going to do, the memory pool is going to scan from left to right and find the first F. Because if this is F, it's not active, and so we can just overwrite. We can just overwrite the data there because it's a dead entity that's not doing anything anyway. So let's add an entity there. And that entity, active, gets changed to true because this is an entity that we're using, and the tag gets set to p. So now the entity doesn't have any components yet, so let's add a component. So we add component C1, and now C1's Boolean gets set to true. And if we want to say, get the component value and change that, I went from bold to not bold. So p.getComponent C1.value is 7. We just change the memory there to be 7. It's so easy. Now let's add a second one. Let's add a Q. Well, we scan and we found that this was an F. So now we have a second entity with a tag of Q. And let's add a component, C2, and give its value here. And then we change its value to 3. And now, if I want to remove a component, all I have to do is change this value here to an F. I don't even need to worry about the data there, right? Whatever data is here, it doesn't matter. I don't need to reset any of that data because this is F, so the entity does not even have that component anymore, so we shouldn't be looking it up. Next, let's say that we destroy an entity. Well, all I have to do is mark it as false, right? It's no longer active. So the only thing the destroying of an entity does is mark it as false in the memory pool. Then later, if I want to add another entity and call it R, well, I'm just going to put it right there because that space was no longer being used by an active entity. And what I do when I add this new one is I zero out all of these values again. And so if I want to add the component, I just do the same thing with this one and set its value to true. So that's how the memory pool works. It's actually like really simple conceptually. And now all of the systems that work on individual components, well, look at this. If I'm iterating through entities, all of the transform components are all contiguous. All of the sprite components are now contiguous. All of the bounding box components are now contiguous. So when I actually do this for each entity, get the component, the transform component, what happens in the cache here? Well, I get this entity's transform and maybe 4 or 5 other entities transform. And so I have far more cache misses here. And so what this means is, just like that example of multiplying things by 3 that we did earlier, now maybe my movement system is 5 times as fast. If I can fit 5 transform components in the cache, then this is literally 5 times as fast. Crazy. All right. Well, that's it. That's it. That's memory pooling. That's cache coherency. It's something, I mean, this is a lot to ask for your project, which is why I didn't make it mandatory. I didn't put it into your assignments because it's a little bit confusing. But I just wanted to show you that this system that we've had the whole time can be changed to use a memory pool. And the really cool thing about the system that we have used so far is that really all we are changing is how the data is stored in the backend, right? In the memory pool and a little bit in the entity manager. None of our game code would actually change if we wanted to use a memory pool. We'd still have entity manager.addEntity, .removeEntity, whatever. All of that would stay the same. None of our game systems would have to change because of this, right? It's mind-blowing how cool this is to me, at least, and how much speed up it can give your system for the cost of just upfront memory. All right, so that is the lecture for today. In the next lecture, we are going to talk about, okay, once you've created, maybe you have your current version of your game, and then you've created, like in a separate Git branch, your like memory pooled version of the game, and now you actually want to profile your code to see where the bottlenecks are, how much faster it is. How would you actually do that in an efficient, safe, modular way in C++? Well, that's going to be the next lecture on Tuesday. All right, so thanks everyone for tuning in. I find this is where my heart really lies, is this sort of low-level optimization stuff. And trust me when I say it could make your game engine 10 times faster. Like, it's insane how fast it makes things. All right, see you in the next one.